Hello everyone, I'm back with part 2 of my IPM video. This will be number 8 in my CO250 series. Although I keep saying these numbers at the beginning, but I know I'm going to need to reorder these after, so we'll see if I need to edit that or something, or you could just ignore me and I'll number them myself later. But essentially, I want to cover a specific example of IPM. I worked out all the details. Took me the longest time to figure out where I was going wrong on this. So I can explain that to you if you'd like, but I'm not going to cover it in this video right now. But essentially, I just have a primal over here. It's an SEF, which is good. That's what we need to run IPM, same with simplex. And then I have my tool over here, and I added my slack variables in. So to start IPM, and I'll read out the numbers to you here, just in case you can't read them very well, and then I'll let you compute the dual yourself. So the C vector here is 0, 1, B vector is 2, 3, and then A is 1, 1, 2, 1. And from there you should be able to compute the dual, so I won't read you those numbers over there. But essentially to start IPM, we need to start with interior points. So I got these interior points over here, and we're just going to check that they're interior points to begin with. So first, for it to be an interior point, obviously it has to be feasible, or else it's not on the interior of the feasible region. So let's check that. We have 1, 1 here. So I have 1 plus 1 is 2, and then 2 plus 1 is 3. So that's good. It's feasible, and it's non-negative, which is also good. But in order for it to be an interior point, we need it to have components that are strictly positive. So I kind of touched on this in the last video. They can't sit on any of the edges, so we need this to be positive. And we have this here. So, because 1 is greater than 0. So this is a interior point. And then we go over here, and I have these two. This is one solution here, because we have our y bar, and then we have its corresponding slack. Now let's check that these are interior points. So I plug in this to make sure it's feasible. Okay, 1, 1, 1 plus 2. Okay, that's 3. Then minus 3 is equal to 0. And then I have 1 plus 1 is 2. Minus 1 is equal to 1. So I know this is feasible. And then in order for it to be an interior point, we talked about this last time too, we have to have that the slack is positive. So we can see both of these numbers here are positive, so that's good. It's feasible and it's an interior point. So I've graphed this out for you. I know this graph looks terrible, but this tripped me up for a while too. But essentially, I've graphed out planes 1 and 2, which are these lines here. And note that this is equality. I don't have the less than or equal to, these are not half spaces. These are simply hyperplanes. So the only feasible solution I have is actually at the intersection point, which is right here, 1, 1. So this is actually my unique feasible solution, and you can kind of think about linear algebra as to why that's true. But essentially, that's it. That's my only solution. So this makes this kind of problem kind of not really reasonable, and that's what happens when you just try and draw something out in 2D space. So just bear with me on this. This is our only feasible solution. It's there. It's got to be optimal. So, and then we have, for my pink over there, we have these two half spaces because we have less than or equal to over here. I didn't draw in the slackness, I just kind of drew it out like this because I feel like it's easier to draw that way. And essentially, they push out this way, so that's why all this pink region is feasible, even in the negative area over here and here, because we have that y is free, so it doesn't actually make a difference if y is negative, so long as it's satisfying those constraints. So we have that, and I've picked out my optimal solution here is going to be over here. We're not quite sure what this is yet, but we'll find out later when I run through IPM. So these are my primal, my dual. I got my interior points so I can start IPM. And then here's my graph. So now we have to get into what I have to do with IPM. So if you recall, the first thing I need to do is set up this big old matrix with all these conditions I need, and then I'm going to solve for dx, dy, and ds. So, okay, what do I need for that? Well, the first thing I need is oh, this marker is so dying on me. Okay, I guess we're going to brown now. That's so sad. A dx equals 0. This is our first condition. You can see this on Tim's notes. So what does this look like? Well, we have that a is 1, 1, 2, and dx, there's just going to be 2 of them. It's going to have the same number as variables x. So we have to have that this equals to 0. Cool. What's our second thing? Well, we say that A transpose minus the identity matrix times dy ds is equal to 0. I explained why in the last video, but now we just get to plug and play here. So this is going to look like, I'm going to put that thing in over here, and the negative identity matrix looks like this. 0, -1. So like this, I don't know if this is actually called the negative identity matrix, but that's just what it looks like there. And then we have two of these guys, dy1, dy2, and two of the ds's for each row. ds1, ds2, like that. And we want this entire thing to be equal to the 0 vector. So we have this. And then what's our third thing? Well, this constraint will look a little bit weird, but essentially we're component-wise looking that s bar times dx bar plus s bar times dx plus x bar times ds, component-wise adding them all together is equal to negative s bar times x bar. So what does that look like? That was just a lot of yapping. So we have s bar over here is 3, 1. So I'm just gonna make it look like this, and I'm just gonna put zeros in here, like I'm kind of overlaying it on the identity matrix. And then I have zeros. Oh, no, I don't want to do that yet. I'll show you that after. And then I have my x bar, which over there is 1, 1, so this looks exactly like the identity matrix, times dx ds. This is going to be equal to, okay, what do I put over here? Well, we have that we want s bar I dxi plus x bar I dsi equals to negative s bar I x bar I for all I in the indices of the columns. So what is this? Well, s bar I times dxi, that's what we're getting over here, and then that's what this part is doing. This part needs to be negative s bar I, x bar I. So I know I have an s bar, and I have an x bar, so I have to compute this. So I'm looking for negative s bar 1, x bar 1, which is equal to, well, s bar 1 is 3, and I have my negative out in front, and my x bar 1 is 1. So this equals negative 3. So that's what I stick up here, negative 3, just like that. And then let's do the second one. S bar 2, x bar 2 equals negative, well, what's my s bar 2? It's 1. What's my x bar 2? It's 1. So this becomes negative 1. So I put that over here. So now we have that this was my A condition, this is B, and this is C. And now this looks like a disaster right now. How am I supposed to solve this? Well, I can actually stick it all into one massive matrix. So I'll show you what that looks like. So, massive matrix. It essentially looks like this. I wrote this out in the last video, but I think it's worth putting in here again, because you should really remember this if we're gonna have a question like this on the final. Something like this-ish, identity here. This is a little bit like confusing notation, but it'll make more sense when I actually write it out. And then this is gonna be dx, dy, ds equals 0, 0, and then this one down here is this guy here. So now we're just going to fill in all these things with the work we did before. So I'm going to fill in, okay, A, well my A over there is 1, 1, 2, 1, and these are all zeros, so I'm just going to put 0, 0, 0, 0, 0, 0, 0. And remember, we have two of these each because I have two variables for my x. So I have dx1 and dx2. And I have two variables for y, so I have dy1 and dy2. And you can see other examples where you maybe have like 3 y's and 3 s's and 3 x's, or maybe you have 2 x's and 2 s's but 3 y's. But this example, we just have 2 of each. So I'm just gonna throw these in there. Oh, 2. There we go. So that's why I have this, and then these ones are all zeroed out. And then this first part here will recover my a dx equals 0. That's entirely captured by this first thing here, these first 2 rows. And now this one here, I'm going to get my a transpose minus identity matrix thing times dy dx is equal to 0. So what does that look like? Well, I can put my zeros here because I don't care about dx in these constraints. And I have my a transpose 1, 2, 1, 1, and negative identity matrix like we did before. So that's cool there. This will, I can put 0, 0, 0, 0 here. So that's good. And then this last part here is a little bit confusing, but I'll just show you how this looks. So remember we got, this is C over here. So this one's A, this one's B, and these 2 rows down here are C. So I wrote out C before. So I'm basically just putting it in here, but because we don't want dy in this constraint, I just have zeros here. So we're not actually doing anything with dy in the middle. So essentially this one was 3, 1, overlaid with the identity matrix. That one was x bar, which is like that. And then we calculated our negative s bar, x bar for each component I over here, and we found this was -3 and -1. So there it is, folks. This is our big, massive matrix that we were supposed to solve. I pray that it won't show up on the exam. I highly doubt it will, because I don't know what we're gaining from solving this in an optimization class by hand. But this is what it looks like, and we can very reasonably be asked to set this up. And maybe we're provided a solution for this after, which I have a solution for this because I have Maple and I ran it in there. And the solution to this is dx bar is equal to 0, 0, and dy, and I don't know why I keep saying bar, this is just dx and dy. 1, -2, and then ds is equal to -3 and -1. So this is the solution I got to this whole system here. These are the directions we want. So, and I'm just gonna plot. We have that this is our x bar here, it's the only feasible solution, but we're starting at y bar equals 1, 1, which is also right here, this pink point. These are the same, but I'm just putting them next to each other. But essentially we're starting here, and now eventually I'll show you what we're doing with this. So our dy bar is the direction we'll be traveling in. So 1 and -2. Oh, now I have to think about how this looks. We're traveling 1 over this way and -2 down that way. So that's like this direction. So this is what dy is telling us right now. It's going in that direction. But we haven't figured out how far, because you can see if I just use the whole thing, maybe it's going all the way out here. I don't know yet. This is just an arbitrary arrow, not accurate depiction. But I just wanted to kind of visualize it for you. So now I have these solutions. What's my next step? Well, I'll refer to Tim's note thing. We have to figure out alpha, so that alpha, want to find, oh, I forgot this marker sucks now. Where's my, okay. We want to find x bar plus alpha dx greater than or equal to 0. So it's still feasible. And we also want to find s bar plus alpha ds greater than or equal to 0. So again, it's feasible for the dual. Remember, y is free, so we actually don't care about y at all. Because we've already made sure it's feasible in here, and it has no non-negativity constraints anywhere. So we want to find an alpha such that this is true and this is true. And there's a whole formula thingy in the textbook to do this. This example is a little bit cheeky because of the fact that this point is unique, I think, is what's doing this. But we're gonna do that now. So just gonna erase up here, give myself some room. In general, you want to find such that these hold strictly. because you're gonna get another interior point, and you're gonna keep getting those interior points as you iterate through and arrive at like a really close but not quite optimal solution. But this example is special, and maybe it's confusing to show you, but I'll go through with it anyways. So I want this condition here. So I want x bar, which is 1, 1 from over there, plus some alpha, and dx bar solve for is 0, 0, greater than or equal to 0. Well, we can see alpha doesn't actually make a difference here because I have this 0, 0 business. So we don't care about this, trivially satisfied. And then let's look at my ds now. So I have s bar, which is 3, 1, plus alpha, and then my ds over here is negative 3, negative 1. So I want this to be greater than or equal to 0. Well, what can I make alpha? If I rearrange stuff, I find that alpha has to be less than or equal to 1. And I always want to choose an alpha greater than 0, and I'm going to choose the biggest alpha I can get. So that's going to be alpha equal to 1 is what I'm going to choose. And this should already have your spidey senses tingling, because if I can get alpha equals to 1, that means I found the optimal solution. This is very, 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 very rare. You will mostly see cases where your alpha you're choosing is between 0 and 1. And again, I think it's just because of this unique solution that I have in this example. But essentially, once we find this alpha such that both of these conditions hold true, I set my x bar plus alpha dx to be equal to whatever this computes to. So instead of alpha, I'm just going to replace it with what I found alpha to be. This is 1, 1, and this one here. I apologize for all the door slamming. I am not going to refilm this because this takes me a long time to do, but generally I try to avoid the door slamming thing, but it's okay. So once I compute this, I find that this is 0. And this is my new slack here. Let's call this s bar bar maybe. This is my new feasible solution, which we see is the same because there is only one feasible solution. And now I have my slack is 0. And you're like, wait a minute, if my slack is 0, that means I must be optimal because there's nowhere else I can go. So let's test that out. What's my y bar now? And I'm only checking y bar because I got to the solution. In general, you don't really have to check y bar. But I want to show you what's going on here. Y bar bar. I probably shouldn't have erased dy. I have it over here now. And so we have 1, 1 for y bar plus alpha, which we set to 1. And this guy here is going to be 1, negative 2. That's our dy that I solved before. What is this going to be equal to? Well, 1 plus 1 is 2. 1 minus 2 is negative 1. So this is my new solution y. And now I'm going to see what happens when I plug this in. Well, okay, I got 2 minus 2 is 0, and my slack is 0. And I got 2 minus 1 is 1, slack is 0. And then if I plug this into my objective function here, I have that 2, 3 times 2, negative 1 is going to equal 1. Okay, that's cool. And what about up here? Well, my c value over there, 0, 1, times 1, 1, this also equals 1. And we're like, wow, this is like weak duality here. We have that the objective values match, so it must be optimal. So we reached an optimal solution. We also found that the slack's 0, so that means it's optimal. So this is really cool. We found something that usually does not happen when we use IPM. We got to the exact optimal solution. But again, in general, most cases, you are going to find some alpha between 0 and 1, not including either of those, because we don't want it to be 0, because that means we're not doing anything, we're not moving anywhere. And we usually can't get 1, because if we can get 1, that means we got an optimal solution. So, say I didn't get alpha equal to 1. Something happened and my alpha, say like I just pick alpha equals 0.5. What then? Well, instead of having this business here, I would have, I don't even care about y bar right now, because I know it's not going to get me what I need. I'm just going to check out, well, actually, no, do you need to compute y bar again? I don't think you do, but we'll see. Plug in 0.5 instead. Okay, what is this going to get me? Well, it's still 1 over here. What is this going to get me? Okay, well, this is going to be 1.5 and 0.5. So this is my new x bar, and this is my new x bar, or s bar. And I have to do that whole massive matrix again with all this stuff. Set up my A0, 0, 0 transpose thing, s bar, 0, x bar, blah blah blah, solve for dx, dy, ds again, and then spits out my thing. So this is 0, 0, and negative x bar, s bar. Spits out a solution, solve for alpha again, rinse, repeat. That's why this algorithm is really, really hard to do by hand, but we do find that it's faster in general, simplex. Again, don't know much details about that, but that is interior point method in a nutshell, even though that was like 40 minutes nutshell. So I hope you learned something from this, and I hope this helps you on the final, and thank you for watching.